Hello, so this is the lecture on human error. This relates to human-computer interaction fundamentally, but also not directly. But it's a relevant topic that I think everybody working in the design space really needs a better understanding of this. All right, so first we're going to start off definition-wise. So what is a human error? So according to James Reason, one of the main error psychologists of our times, it's a generic term to encompass all those occasions in which a planned sequence of mental or physical activities fails to achieve its intended outcome, and when these failures cannot be attributed to the intervention of some chance agency. So there's a lot of pieces going on here, but what we have is basically a planned sequence of activities or tasks, actions. They're planned by the human, so that's where we get, intention, intent. And then there's an intended outcome, and then a disqualifier at the end that failure that cannot be attributed to some other intervention, right? So it's a good definition, but it has a few different parts that are worth kind of examining. So first, it's outcome dependent, and that is pretty typical. Well, when we think of a human error in ourselves or in other things, a lot of times it's because there's some negative outcome. Now, that doesn't necessarily mean that it's a completely extrinsic outcome. So, for example, you make a mistake on doing something, but nobody else was there, and you feel shameful or embarrassed by it internally. That still is an outcome. So it doesn't necessarily have to be something attributable to external behaviors or demonstrations. Then he uses the term chance agency. This is an interesting subject. So basically what this is something else intervened, some aspect, you were driving down the road and let's say a soccer ball rolled into the road, you swerved to miss it, hit another car. That could be, that's not a human error per se, that's the intervention of some chance agency. And I'd be remiss if I didn't involve a little bit of philosophy. So looking at a theory by Bernard Williams called moral luck, this adds an interesting ethical feature to this. So under moral luck, Williams argues that there are certain actions that their immorality is only dependent on outcomes. He uses the example of somebody who drives drunk home and gets home safely. The next night they do the exact same thing, but at one point in their trip they had swerved a little bit over the line. That first night nothing happened. That second night a person was standing there. Does the action's morality change as you look at that outcome? So that's another aspect that I think is useful just to kind of reflect on and think about in terms of how that applies to human error. And also in terms of human action, right? We just want to acknowledge that in this definition, the term planned is really doing a lot of heavy lifting in this definition, because some of us may argue that when we have made an error, we certainly did not have a planned sequence of activities. So, but it's worthwhile to consider, and it's probably one of the better definitions that we found. So now here's the next question. Can you intentionally err? So what about intentionality? So the function of human error is supposed to be that you did not intend for that to happen. So in that instance, that's where we need to decouple that. So it's possible that you cannot intentionally make an error. You can intentionally do the wrong thing, uh, you know, and that's kind of what we get into malicious compliance or sabotage. But then the two other questions we need to understand is, how do we know we made an error? And how can we know why we made an error? So those are two distinctions. How do we know we made an error? Usually that's some kind of an outcome. It's something, it's part of our feedback from the world, right? We take an action, something occurs, and we attribute it correctly or incorrectly to ourselves or to something else. But if we think about reflectively, how can we know why we made an error? That really becomes a lot more tricky. After the fact, I think a lot of us would say we can look at what we did and identify what we did wrong. That's possible with the new knowledge, the knowledge of the post-incident, the hindsight is 2020 thing. So in the moment, we maybe didn't think we were doing something wrong. And so we get into that tricky thing of we're always judging ourselves by a standard of knowledge we didn't have at the time. And that's just an important thing when we consider design and how our users will interact with these systems. We want to make sure that that we give them feedback. This is why we have error messages and confirmation prompts, those kind of things, to really help that self-focus. Okay, so then there's also the aspect of inevitability. So some amount of human error is always going to occur. So what can we do? There's two kind of directions for this. From a human factors perspective or a design perspective, right? We improve the design of the system so that it complements our human capabilities. This will be kind of a stronger focus on usability and efficiency. But for like user experience design, we're also looking to do this. If something feels effortless in your interface, that's going to be a more pleasing experience. And then the second piece here that isn't reflected in the human factors, right, is iteration and evaluation. We need to be able to evaluate those designs and in order to improve them. The second aspect here is human reliability. So this is often used in industrial settings, but it's more of a predictive method. So how do we assess the human contribution to the overall system risk? So this is, yes, we know there's going to be human errors. If a human error happens at one of these 5 decision points, what does that do to the overall probability that we're going to have an issue? Like I said, this is more often done in systems or industrial engineering spaces, but it is something that we can be asked to do, and sometimes it's valuable to look at it and to extrapolate on the broader tasks and different things that we have to do, so that so we can kind of pull that apart and try to identify issues, because you can do that also with human reliability. With that kind of a focus, you can step back into the task and deconstruct it. So I always like to include this graphic in nearly every presentation that I do, because I think it really captures an important point, where humans, I would say the resiliency of humans, which we'll get into shortly, is also matched by humans' creativity and variability in how we do things. And you just, engineering can only take us so far. fundamentally, we have to design systems that are resilient to human error, design processes and interfaces so that they minimize human error. But that's probably the ballgame. That's probably as best as we can get. And I think that that's an important distinction to make, is that it doesn't matter what system you have, doesn't matter what neat technology you're using, it still can be beaten by the human. And that's where we come in. All right. So human error and risk. Okay. This is something that I wanted to, that I also bring up in most presentations, which is the percent of incidents where human error was a root cause. As you'll see here, the percentage of incidents where human error was a root cause are significant. And if you track back through history, have been increasing. And the reason I note this is because there is a push using these data points to remove the human from the system. And that's really taking the wrong lesson from the data. So if you were to go back 100 years and compare human error versus system or engineering failure, that number would be a lot more evenly spread. But in the ensuing century, we've achieved significant increases in engineering reliability, design, materials. All of those things have improved significantly. Well, humans don't improve that fast. We evolve on a biological timescale, which is significantly longer. And so it's really not a question of humans are extraordinarily error prone. What it is an instance where the denominator has shrunk. The overall number of incidents are down. And of those number of incidents, human error has a larger percentage of them because simultaneously two aspects. One, like I said, humans aren't changing at the rate engineering and materials and all that is. Number two, human factors has not been integrated well enough in most situations, and human human-centered design principles have been widely ignored or kind of shunted off to the side in favor of whatever new hotness, automation, or AI that has come out. So I would say, the one thing that's missing in this aspect is, okay, how many of these human errors were related to a poor human-centered design, or how many of them were because the human capability was mismatched and the design was not sufficient? That would be the piece of data I would like to have. So now, this is an important distinction. So can human error ever be a root cause? So looking at all of the problems or all the situations that have coalesced to have an incident occur, there's a question: can human error ever be a root cause? And typically in accident investigation, cause analysis, and those kind of aspects, that answer is no. So in human factors, we have a saying: there is no human error, just bad design. And this is where we go back to those first couple slides about what does it mean to have an error and what are the pieces of it. If humans do not intend to err, but error still occurs, is it the human's fault? And I love this image, right? So this, there's countless wacky design images on the internet, but I love this one. If a bicyclist was just looking at the indicators that were painted on the surface and then ran into one of these poles, is that a human error? Depends on what you think. Some people might say, well, yeah, they should have been watching the whole area. Yeah, that'd be prudent, but is it necessary? Typically in human life, when we have signs or indicators like this, we are supposed to look at them. That's why they're there. And we are supposed to follow them. So you get into kind of that distinction, right? And then like I said, in accident investigation and cause analysis, typically what you'll hear is if human error is your root cause, you didn't go deep enough. There's something that caused the human error. And so you need to get into what that is. So again, looking at what we know, to err is human. Every human action is subject to imperfection. Even highly trained, highly skilled, highly proceduralized actions tend to fail 1 out of 100 or 1 out of 1,000 times. Certain contextual factors may increase or decrease that likelihood. What's important also is the same qualities that make human actions error-prone also afford resilience. So humans spontaneously recover from most errors. Internal self-monitoring and our external feedback loops can help correct the course. So examples like catching yourself while mispronouncing a word or correcting while starting to lane drift. Also, most human errors are not single point failures. Actions are part of a bigger sequence of activities with checks, corrections within a context or a system, and that all needs to be noted and monitored as we design. So go ahead and pause the video and go ahead and read through this, and then I go ahead and come back and I'm going to just summarize it. So what this quote is basically saying in a very kind of roundabout, circuitous way is that what our brain does in terms of integrating all of the sensory and perceptual inputs that we have is astounding, in that it takes all of this raw data, sorts it, categorizes it, decides what to move to working memory, what can be deleted, what we need, all of that, and can build or populate schemas, all of those aspects. And it does it in milliseconds. But what this quote also says is, once all of that is done and all that perceptual input has been grouped and categorized, and we have some useful properties or characteristics, that those, I guess, ensuing schemas, or whatever we want to call them, cannot be juggled or recombined or processed in anything like the way our sensory inputs work. And I'm still not sure why, but it's part of just the mystery, but also the reality that human cognition is messy. We don't totally know why things happen or why they don't, and we aren't always set for how they, the different ways that people will perform tasks. That's why we do user research and why we do iterative design, is because we don't know. Even experienced designers that have designed hundreds of interfaces cannot predict what will happen once a user gets a hold of it. And that's an important distinction, and an important thing to keep in mind. So now we're going to go into a few of the taxonomies that are relevant. So first, Swain and Gutman's THERP. This is a human reliability analysis methodology predominantly used in the nuclear power industry, but it was one of the initial ones back in the 50s and 60s. Then we have Rasmussen's skill rule knowledge framework. This argues that actions fit into specific bins of cognitive performance. And then we have kind of a mashup of James Reason's error taxonomies with Norman's action theory. And we get further categories of slips, lapses, and mistakes. All right, so Swain and Gutman. So within THERP, the technique for human error rate prediction, HRA method, there are a handful of errors that can be marked in the analysis. Errors of omission, so you failed to do something you were supposed to do. Errors of commission, you did something you weren't supposed to do. Sequence errors, you do something in the wrong order, or timing errors, where you do something too slowly or too quickly. And this was the dominant thinking of error psychology for a long time, until Rasmussen came around in the 70s and 80s. So, and it makes sense, right? These are, I think, when we think of human errors in ourselves, these are relevant. These are things we would do, but they're not the whole picture, right? None of these specify or even have an implication of the why the error happened. So an error of omission, you failed to do something that was required of you. Why? The failure isn't the problem. The inciting event of the failure is the problem. So that's one of those shortcomings of this approach. So then looking at Rasmussen's skill, rule, knowledge framework. So Rasmussen theorized that most human decision-making and behavior falls into one of three bins. We have skill-based, rule-based, and knowledge-based behavior. Basically, when we're babies, everything's knowledge-based. We're trying to figure out different things. As we stick things in our mouths or whatever, we start to develop rules. And then those rules then inform our practice. And if it's, to open this doorknob, I have to pull instead of push, that becomes a rule. And then over time and repetition, it becomes a skill-based behavior. So something that's largely automatic and doesn't really require cognitive resources. And then in the inverse, skill-based is something you've done a ton. Rule-based, okay, you've done this action, but maybe this is a unique situation, so you have to take a step back and apply some rules to figure out what to do. And knowledge-based is when you don't have the skill practice, you don't have the rules, you're just having to use logic and problem solvings. And Rasmussen's argument was also that as we move up or down the framework here, the more we go up the framework, it requires greater attention to a task, and our error rate increases. So knowledge-based errors have the greatest level of error. Rule-based have a slightly lower, skill-based lower still. And so this was Rasmussen's thinking, and is still a fairly dominant way of thinking for a lot of standards or guidelines that you may come across. But it's not, again, the whole picture. So looking at Reason and Norman's error taxonomy, we get some other useful categories. And these are helpful because they merge some of these different aspects of the previous two and help give us some more psychological realism. So a slip, good intentions, you had the correct mental model, but you happen to do something wrong. So it's an error of commission. You're doing something, but you have the right mental model, so it's not a rule-based error. So again, it prompts that, okay, we know what we've got here, but we need to dig deeper to find the why. A lapse. So you have a good intention, right mental model, but failed to do something. So this is an error of omission. Often this is a memory type concern. Then mistakes, good intentions, wrong mental model. You did do something, it's an error of commission. You were in the wrong mental model, so it's a rule-based or knowledge-based error, potentially. And then violations, these are kind of the exceptions, right? These are willful circumventions. This isn't an error in a traditional sense. This is you intended to do something that you knew was not what you were supposed to do. And it doesn't necessarily have to be malicious intent. It can also be aspects of heroism. I'm going to do this to save the situation, or you have a mentality of there's a better way to do this. So as you're going through and using the taxonomies, it's important to note they're not independent of each other, and they shouldn't be used in that way. So they have different applications. So Swain and Gutman's taxonomy, we have, it's easier to understand when something failed to do a prescribed action than to think about all of the potential things they could do. It also has some valuable tie-ins to other methods like HAZOP or some of the OSHA methods that maybe use this error of commission dichotomy. Rasmussen's taxonomy gives us the ability to look at skill levels and to start exploring automaticity and training in a way that Swain and Gutman's doesn't. And Reason's taxonomy gives us the ability to look at intentionality, but also gives a little bit more breadcrumbs for like what could have went wrong. Is this a memory issue or something else going on? So you need different information to come to an answer for each taxonomy, but your greatest benefit is going to be to use them all together. Now, as we look at cognitive mechanisms for human error, so we have memory issues, attentional constraints. People forget attention is your cognitive fuel. Let's say it's the thing, the resource you have. So as your attention shifts and you have constraints on it, you may get errors because you just simply can't assign resources to that task. Vigilance and boredom. This is a huge problem for a lot of different job tasks and just general day-to-day tasks. Lack of experience. Also too much experience. We have the keyhole effect, where you hyper-focus on what you can see and do not consider the broader context. Heuristics and biases, like the things that came out of Kahneman and Tversky's research. And confusion. And this isn't an exhaustive list. These are just a handful. So James Reason also gave us the Swiss cheese model, which also led to defense in depth. So the idea of the defense in depth philosophy, which is echoed by the Swiss cheese model, is that for an accident to happen, there typically have to be many failures in a lot of different layers of the system. And so there are multiple different barriers to stop human error having severe consequences. And this was a really critical theory. And while sometimes people will joke about it, it is still valuable. Here's another example that's a little bit more relevant to our recent periods, right? Here's the Swiss cheese respiratory virus defense that started circulating around COVID. And what's important is how our jobs as designers or human factors professionals relate to all of these. So the analogy I've always used is human factors or design or whatever. Our job is to determine the size of the holes in the cheese and where we're going to put the holes in the cheese. Human reliability analysis is the act of spinning these slices of cheese on, let's say, a central axis and counting the times that the holes line up and trying to get to the bottom of that. So in that instance, you can look at human error and human reliability as being two sides of a separate coin. Then we also have different error consequences. So if the potential result matters, so does recovery. So do we look at this as, what determines a blunder? We have minor recovered errors, blunder, which I still love that they use blunder in this and want a better definition. Minor incident, major incident, accident, severe accident, because we have consequence was high. And so this is where we get into that first, going back to those first principles about okay, if the outcome matters, then the recovery should also matter. And that's one of the things that we see a lot in industrial spaces, especially as we see like safety one versus safety two or just culture type theories. It's about trying to credit the recovery as well as the result. So here's a couple of other definitions just for your relevance. I'm not going to really go through these a lot. Feel free to pause it as needed and read through them, but these are just good to know in case you work in a domain where having some of these standard definitions are relevant. So feel free to pause it if you need. Okay, so now we're going to go to active and latent errors. So active errors, something hit the fan. These are unsafe acts, failures of technological function, or human errors that become the local triggering events that afterwards are identified as the immediate causes of an accident. Considered to have immediate effects, so operations error. This is an active error. You can trace it. You know the causal chain and the aspects that led to the situation. But then you have latent errors, and these are far more common. This is the accidents waiting to happen. So it's a result in latent conditions in the system that might become contributing causes for the accident. They're weak links, let's say, and if the right scenario comes along, they will fail. They're present within the system as unnoticed conditions well before the onset of a recognizable accident sequence. This is very common in accident investigation, where you will come across aspects of operations or organizational performance or things, and when they become a problem, you trace it back and, oh, that's always been a problem. It just hadn't bitten you until now. And so that's an important distinction to make as well. So latent errors, we employ another James Reason term, the resident pathogen analogy. So industrial accidents often result from a combination of errors, so like a perfect storm. The more resident pathogens in a given system, the more likely that an accident will occur. So the more latent errors that are there, the more weak links, the more likely that an accident will occur. The more complex the system, the more pathogens it can contain, and often it does contain. A simpler system with poorer defenses is more vulnerable to pathogens than a more complex and better defended system. The higher the hierarchical level of an individual, the greater his or her potential to generate pathogens. This is an organizational thing where we see or a higher level in the org chart folks can typically have outsized impact on the generation of latent errors. And then the pathogens present in a system can be detected a priori, unlike active errors that are difficult to predict and are often only found a posteriori. So the pathogens can be detected long before through audits or assessments, different methods there. But active errors you typically aren't aware of until they happen. So how do we prevent it? You beef up the difference, right, is you beef up your immune system and health versus living in the bubble. So Reason argued that it was more impactful and interesting to focus on the detection and elimination of these pathogens rather than active errors. Now going into performance shaping factors. So this is an overly formal term that you'll hear in certain domains, especially in industrial or nuclear power, aviation, these kind of things. Fundamentally, they are the factors that influence the performance and error likelihood of human activities. When we talked about the cognitive mechanisms of error, memory, vigilance, those kind of issues, they're all performance shaping factors. We typically group performance shaping factors along two spectrums: internal, which are our internal human attributes, such as skills, abilities, but also our latent and inherent characteristics. Potentially, some folks have a better memory than others. Some folks might perform very well under pressure. Those kind of intangibles. And then we have external PSFs. So these are aspects of the situations, tasks, or plant characteristics that influence the ability of the human to carry out those activities. So this could be environmental aspects. This could be the interfaces designed poorly, the procedures are confusing, the training was insufficient, etc. What's also important to note is PSFs may enhance performance. So they don't just have a negative impact on our performance. So good procedures, training, or interfaces may help the operator navigate an upset condition better. But they also can degrade performance. High complexity and high stress tend to slow operator response, which becomes a problem if you need a certain speed of response. And in terms of a list of PSFs, there are many out there, from some as simple as 8 all the way up to hundreds. And realistically, it's probably an infinite number. And then you get into the combinations of them. It gets quite complex quite quickly. All right. Well, thanks for watching. I hope this was a valuable dive into human error for you. And I hope it spurs better designs. Thanks.